Section: Introduction. In this section, we introduce the significant advancements in large language models, LMs, that have resulted from scaling. We note that current scaling laws mainly depend on the size of the pre-training data and the number of parameters in the models. However, we also explore another aspect of scaling, the amount of data in a datastore that retrieval-based LMs use during inference. These models can directly pull information from the datastore to help generate their outputs. Retrieval-based LMs offer several advantages, including better factual accuracy, effective adaptation to specific domains, clearer credit attribution, and more efficient use of parameters. Yet, most previous research on these models has relied on datastores created from a single source, like Wikipedia, which typically contains a few billion tokens. Although there have been efforts to create larger datastores, such as Retro, which has around 1 trillion tokens, these studies often use proprietary data and custom architectures, limiting their evaluation scope. Consequently, we still do not fully understand how scaling the datastore impacts the leading retrieval in context approaches across various tasks. To address this gap, we have developed MASSIVEDS, a massive multi-domain datastore that includes 1.4 trillion tokens from both general web data and specific domain data. This datastore serves as the foundation for our scaling study. One of the main challenges we face in examining datastore scaling is the high computational cost associated with building datastores that consider all possible combinations of factors, such as the size of the datastore, the type of data included, random sampling seeds, and different data processing methods. To make our study more manageable, we have designed an efficient pipeline for constructing datastores that significantly reduces the computational resources needed while still being comparable to standard methods. Using this pipeline, we systematically assess how scaling MASSIVEDS affects retrieval-based LMs with different numbers of parameters and amounts of pre-training data. In addition to language modeling, we also evaluate a variety of downstream tasks, including general knowledge question answering, domain-specific question answering, and reasoning tasks. Our findings reveal that scaling the datastore consistently enhances both language modeling and certain downstream tasks, depending on the specific task, similar to the trends observed with data and parameter scaling. Notably, for knowledge-intensive tasks, a smaller retrieval-based LM can outperform larger models that rely solely on language modeling. Furthermore, since indexing a datastore is less expensive than training on an equivalent amount of data, retrieval-based LMs can achieve better scaling trends in terms of computational efficiency. They often deliver superior performance compared to LM-only models at the same training cost. Our analyses demonstrate that retrieval-based LMs can automatically pull in domain documents relevant to the query, allowing them to benefit from larger and more diverse datastores. Additionally, implementing data quality filters and improved retrieval techniques can further enhance the scaling trends we observed. Overall, our results indicate that the size of the datastore should be considered a crucial factor in evaluating the efficiency and performance trade-offs of LMs. To encourage further research in this area, we are making MASSIVEDS available to the public, including the raw data, embeddings, and indexing, along with all the code necessary for our evaluation suite and the efficient study of datastore scaling. In the following section, we discuss related work on retrieval-based LMs. Unlike parametric LMs, which only utilize data during training, retrieval-based LMs can access data from a datastore during inference. We focus on retrieve-in-context language models, RIC-LMs, which retrieve a small set of documents from the datastore and combine them as input for the LM. This approach is straightforward and allows the use of readily available retrievers and LMs, even when only black box access is possible. Previous research on retrieval-based LMs has often concentrated on specific aspects like factual accuracy and attribution, typically using limited-size, single-domain datastores such as Wikipedia. The exploration of scaling the datastore itself has been relatively limited, with a couple of notable exceptions. One exception is the retro transformer architecture, which created a 1.75 trillion token datastore from proprietary data. However, the Retro and its subsequent versions primarily used this large datastore for language modeling evaluations, while relying on a smaller, task-specific Wikipedia datastore for downstream tasks. Since Retro-based datastores are not fully open-sourced, replicating this work to evaluate the effectiveness of datastore scaling is challenging. Another exception is Sphere, an open-source datastore with 90 billion tokens curated from CCNet. However, evaluations on downstream tasks like Kilt suggest that Sphere does not consistently outperform a smaller, in-domain datastore like Wikipedia. In contrast, we present the first comprehensive study on the downstream performance of trillion-token scale datastores, including an analysis of optimal scaling trends using retrieval-based LMs with various datastore sizes, model sizes, and pre-training data. Our work is fully open source and can be replicated with limited computational resources, making research on trillion-token datastores more accessible to the broader community. Section Summary. In this section, we explore the scaling of retrieval-based language models, LMs, by introducing MASSIVEDS, a datastore containing 1.4 trillion tokens from diverse sources. Our findings indicate that increasing the size of the datastore enhances performance on various tasks, particularly knowledge-intensive ones, and allows smaller retrieval-based LMs to outperform larger LM-only models. We also highlight the efficiency of our datastore construction pipeline, which facilitates systematic evaluation of scaling effects while being computationally accessible for future research. Section: MassiveEDS and our datastore scaling pipeline. In this section, we discuss MassiveEDS and our datastore scaling pipeline. MassiveEDS is a trillion-token datastore that includes both specialized domain data and general web data. The domain-specific data is gathered from specialized sources, which tend to be smaller but of higher quality. We collect data from a variety of rich domains, including books across different genres, open-access scientific papers, encyclopedic articles, community Q&A from Stack Exchange, code from GitHub, mathematical content, and biomedical articles. In contrast, the general web data is obtained from common crawl snapshots taken at 5 different times: July 2019, May 2020, April 2021, May 2022, and June 2023, as well as from C4. When we study datastore scaling, we need to create datastores of different sizes and compositions from the raw text corpus. This process involves several steps. First, we filter the data, which includes removing duplicates, cleaning the data, and applying quality checks. Next, we perform data subsampling, where we randomly select a fraction of the text corpus to reach the desired size. Then, we index the data, which means we embed it using an auxiliary model and create a searchable index. After that, we retrieve documents using this index to find the top 5 relevant documents for each test query. Finally, we evaluate by using these top 5 documents to enhance our retrieval-based model. A straightforward method would be to execute these steps in the order mentioned for each datastore, creating separate datastores for all combinations of subsampled sizes, random seeds, and other experimental variations. However, this naive approach is too computationally intensive at the scale of 1 trillion tokens because it repeats costly operations. To address this, we developed the MassiveEDS pipeline. The main idea is to rearrange the operations so that the most expensive ones, indexing and retrieval, are conducted only once at the beginning and then shared across all subsequent datastore variations. We perform other operations, like subsampling and cleaning, as late as possible to avoid repeating steps unnecessarily. To facilitate this, we first retrieve a larger number of documents for each query and then apply the subsequent operations to these sets of documents instead of the entire datastore. This approach significantly reduces our computational needs, allowing us to conduct the datastore scaling study within a reasonable budget. In the appendix, we demonstrate that the results from the MassiveEDS pipeline are likely to be equivalent to those from the naive pipeline, with the randomness stemming from the subsampling process. We provide further details about the MassiveEDS pipeline steps and configurations in the appendix. Regarding the number of tokens in the datastore, we plot the datastore size by multiplying the total number of tokens in the raw data pool by the subsampling fraction. A more precise representation would involve the number of tokens in the filtered data pool. However, we do not know this size since we filter data on the retrieved documents for efficiency. Consequently, the number of tokens we display is proportionally larger. For instance, if we filter out a fraction of the data, the actual number of tokens should also be adjusted accordingly. Since we use a logarithmic scale for the datastore size, this results in a constant shift that does not affect the scaling trends. In terms of model details, we utilize Retriever-MS Marco, which represents each document in the datastore as a dense vector, as our retriever. We explore the choice of retriever in the appendix and find that Retriever-MS Marco performs comparably to, or even better than, more recent larger retrievers. We enhance our input examples with retrieved documents in 256-word chunks. We assess datastore scaling performance using the Llama 2, Llama 3, Pythia, and Olmo model families. For evaluation, we consider both language modeling and downstream tasks. We evaluate language modeling perplexity using data from two domains: general web data sampled from REDPAJAMA and scientific paper data from S2ORC. For downstream tasks, our evaluation includes general knowledge, medical, math, and science domains, covering tasks such as Trivia QA, which consists of trivia questions with answers from Wikipedia and the web; natural questions, which includes search engine queries and human annotated answers from Wikipedia; massive multitask language understanding, which features general-purpose reasoning questions; and MedQA, which comprises medical multiple-choice questions from professional medical exams. Section Summary. In this section, we introduce MASSIVEDS, a trillion-token datastore that integrates both high-quality domain-specific data from various sources and general web data from common crawl snapshots. We describe our efficient MASSIVEDS pipeline for studying datastore scaling, which optimizes computational resources by reordering operations to minimize redundancy, allowing us to conduct extensive experiments on a modest budget. Additionally, we outline our evaluation methods across language modeling and various downstream tasks, utilizing models like Llama 2 and Retriever-MS Marco for effective document retrieval and performance assessment. Section: Implementation Details. In this section, we outline our implementation details. For our evaluation involving retrieval, we combine the top 18 documents in reverse order, ensuring that the higher-ranked documents are closer to the query. When assessing downstream tasks, we utilize a method called 5-shot prompting, where we place the retrieved documents before the few-shot examples, followed by the question. We do not use re-ranking in our main experiments, but we will examine the impact of re-rankers in a later section. Additional information, including our decontamination measures, can be found in the appendix. Our first finding is that scaling the datastore significantly enhances language modeling. The figures illustrate how perplexity changes with datastore size for general web content and scientific papers. We observe that retrieval is always advantageous for language modeling. The models that rely solely on language modeling show the highest perplexity across all datasets. Increasing the datastore size consistently lowers perplexity without reaching a limit, indicating that further increases could lead to even more improvements. Notably, scaling the datastore allows smaller models to outperform larger language-only models. For example, when retrieving from the largest MASSIVEDS datastore, the Llama 27B model surpasses the performance of the larger LLAMA 213B model. Interestingly, we find that Llama 38B performs worse than Llama 27B on the Red Pajama dataset. We discuss possible reasons for this in the appendix. Our second finding is that scaling the datastore enhances performance on various downstream tasks, although the extent of improvement varies by task. The figures show performance across 4 downstream tasks as datastore size changes. We see significant gains in knowledge-intensive question-answering tasks like NQ and TQA, where retrieval-based language models outperform those that rely solely on language modeling at all scales, with performance consistently improving as datastore size increases. For instance, the Llama 2.7b model, when retrieving from fewer than 100 billion tokens, can outperform both its 13b language-only counterpart and the more capable Llama 3.8b on TQA and NQ, highlighting the effectiveness of knowledge storage in the datastore. In the case of MMLU, which requires reasoning across multiple subjects, we see consistent performance improvements with larger datastore sizes. However, results for MED-QA are mixed, with only the smaller Llama 2.7b model benefiting from datastore scaling. In both cases, the smaller model does not surpass the larger model, likely due to the complexity of the tasks and the limited availability of relevant data. Both MMLU and MED-QA focus more on reasoning than on simple factual recall, which presents greater challenges for both the retriever and the language model. Additionally, MassiveEDS contains only a small selection of web data and medical papers, which may not provide all the necessary information for these tasks. We plan to explore better data sources for these tasks in future work. Next, we investigate how performance varies with the total compute used during training and find that retrieval-based language models achieve better compute optimal performance compared to those relying solely on language modeling. Regarding the use of intermediate checkpoints, we utilize the intermediate checkpoints from Pythia and Olmo to estimate models trained on different amounts of data, as detailed in the appendix. These checkpoints follow the same learning rate schedule and have a maximum number of training steps that meets or exceeds the actual steps taken, which means their performance might be lower than what could be achieved with the same compute. However, pre-training language models from scratch for all combinations of model sizes and training data amounts is too costly for an academic budget. We also explain how we calculate flops for datastore construction and pre-training in the appendix. Constructing the datastore is much less expensive than pre-training because it only requires one forward pass through all tokens in the datastore using a small retriever, while pre-training involves both a forward and a backward pass with a potentially larger language model. Since we use a flat index, no extra operations are needed during indexing, so the flops for constructing the datastore equal those for embedding. We note that other indexing methods, like inverted file indexing, may require more flops during construction but fewer during inference. We first concentrate on the compute used during training and will discuss inference costs later in this section. We present the scaling curves for retrieval-based language models and language-only performance on downstream tasks, highlighting the optimal points for both settings in red and blue, respectively. Section Summary. In this section, we evaluate the impact of datastore scaling on language modeling and downstream task performance. Our findings indicate that increasing the datastore size significantly reduces perplexity and enhances model performance, particularly in knowledge-intensive tasks like question answering, where retrieval-based models outperform their LM-only counterparts. We also discuss the computational efficiency of retrieval-based language models compared to traditional models, highlighting that datastore construction is less resource-intensive than pre-training. Section. Finding 3. Retrieval-based LMs outperform LM-only models for the same compute budget. In this section, we present our findings regarding the performance of retrieval-based language models, LMs, compared to traditional LM-only models. Finding 3 reveals that retrieval-based LMs perform better than LM-only models when we use the same amount of computational resources during training. This suggests that shifting some of the computational load from pre-training to building a datastore can enhance performance. We believe that storing factual knowledge in a datastore is more efficient than having the model memorize this knowledge during training. However, this assumes that the LM has enough capacity to effectively use the retrieved information. If it doesn't, the LM might struggle to make use of the retrieved knowledge, which we will discuss further in Finding 5. Finding 4 shows that even less powerful language models can gain significant advantages from retrieval when dealing with tasks that require factual recall. Interestingly, we found that retrieval-based Pythia models, which were trained on up to 300 billion tokens, and OLMO 1.7 models, trained on up to 2 trillion tokens, exhibit similar performance trends on Trivia QA and NQ, despite Pythia being trained on less and lower quality data. Both Trivia QA and NQ focus on factual recall without needing complex reasoning. When the correct information is provided through retrieval, the LM only needs to pull out the answer. This indicates that the ability to extract factual knowledge for straightforward question answering develops early in the training process. Finding 5 indicates that retrieval can be beneficial for reasoning-heavy tasks when using capable Olmo models, but it does not help less advanced models like Pythia. Our observations show that scaling the datastore provides minimal benefits for Pythia on tasks like MMLU and MEDQA, where performance remains close to random, even with a model size of 12 billion. In contrast, Olmo, which is trained on higher quality data, consistently benefits from retrieval in both tasks. We hypothesize that training on better data, as Olmo does, could enhance the model's ability to leverage retrieved documents for reasoning-intensive tasks. Additionally, having access to the right data sources for the datastore is crucial. For instance, we see fewer advantages from retrieval on MMLU and MEDQA compared to Trivia QA and NQ, suggesting that MMLU and MEDQA may require more specialized data, like relevant textbooks for MMLU and biomedical literature for MEDQA, which are not currently included in MASSIVEDS. We also discuss the inference cost. Our study on compute optimal scaling primarily focuses on training costs. When we prepend retrieved documents in context, it increases inference costs due to the longer context and the extra computation needed for the search. However, we can reduce inference costs by using a smaller LM, especially since a smaller LM enhanced with a datastore can perform as well as or better than larger models on certain tasks. We note that there is ongoing research aimed at speeding up retrieval searches and creating efficient serving strategies for retrieval-based LMs. We plan to explore inference compute optimal scaling in future work. Finding 6 shows that MASSIVEDS either matches or outperforms single-domain datastores. Previous studies typically used a single-domain datastore that aligns with the downstream task. However, it can be challenging to create a datastore that perfectly fits a downstream task, and even if we succeed, it limits the model's generalizability. In our comparisons, MassiveEdge significantly outperformed these single-domain datastores in language modeling, TQA, and MMLU, while matching performance on NQ and MEDQA. Our results indicate that the retriever tends to pull from the relevant domain even when out-of-domain data is present. For example, for NQ, it retrieves more frequently from Wikipedia and web sources, while for MEDQA, it pulls more from scientific papers. This shows that the retriever can remain robust against out-of-domain data, aligning with similar findings in other retrieval-based models. Overall, these results suggest that using broad datastores like MassiveEdge can enhance performance across various domains, moving us closer to developing general-purpose retrieval-based models. Lastly, we address the effects of re-ranking. Retrieving the most relevant documents from a large datastore is a complex challenge. To understand how improving the retrieval process affects datastore scaling, we first retrieve 500 documents from CONTRIEVER, then re-rank them using a more complex model, and finally select the top 22 re-ranked documents for evaluation. We utilize a cross-encoder re-ranker that evaluates a combination of a query and document to produce a similarity score. We chose a specific cross-encoder model trained for passage ranking. Additionally, we employ a lexical oracle re-ranker, which uses the correct answer to set an upper limit on the potential benefits of a better re-ranker or retriever for knowledge-intensive question answering. Our findings show that while the cross-encoder-based re-ranker improves performance on TQA and NQ, there remains a significant gap between it and the oracle re-ranker. This suggests that enhancing either the retrieval or re-ranking processes could further improve the performance of retrieval datastores. We recognize that improving the retriever for more reasoning-heavy tasks like MMLU and MEDQA is still an open question, which we will address in future research. Section Summary. In this section, we find that retrieval-based language models, LMs, outperform LM-only models when given the same compute budget, suggesting that storing factual knowledge in a data store is more efficient than memorizing it in model parameters. We also observe that even weaker LMs can significantly benefit from retrieval in knowledge-intensive tasks, while more advanced models like Olmo show improved performance on reasoning tasks when utilizing retrieval. Additionally, our results indicate that broad data stores like MassiveEDS can enhance performance across multiple domains, and improving the retrieval process could further boost the effectiveness of these models. Section: Effects of Datastore Filtering. In this section, we address the effects of datastore filtering, focusing on data decontamination. Data decontamination is essential when we evaluate language models, LMs, particularly retrieval-based LMs that might pull test data directly during inference. By default, we implement decontamination by filtering out documents that have an 80% or higher similarity based on 13 grams for downstream tasks and a 32-gram longest sequence overlap for perplexity, which we refer to as standard decontamination. Previous studies, like Retro, only applied the 80% 13-gram similarity for decontamination. However, we have discovered that including the 32-gram longest sequence overlap is vital for eliminating nearly identical documents. To explore how different levels of data decontamination affect our results, we compare standard decontamination with two other approaches: 1. No decontamination, and 2. Aggressive decontamination, which uses an 8-gram longest sequence overlap for all tasks. This aggressive method is a strict filter since 8-gram overlaps are common even among documents that are not very similar. We report the performance of the Llama 2.7b model on language modeling and the natural questions dataset using these various decontamination methods. Our findings indicate that language modeling performance is significantly better without decontamination, and it declines with more aggressive decontamination methods. This suggests that the advantages in language modeling mainly come from lexical overlap. Nevertheless, retrieval still enhances language modeling performance even after aggressive decontamination, where no more than 8 continuous words overlap. This indicates that semantically similar retrieved documents, even with minimal lexical overlap, can still improve language modeling. We also note that decontamination does not greatly impact natural questions performance, likely because there is less contamination in the datastore for this dataset. Interestingly, we observe that decontamination reduces performance with smaller datastores but improves final performance as the datastore size increases. Next, we examine data quality filtering in the appendix, where we analyze its impact on MASSIVEDS. We consider global data deduplication and a combination of 3 filters adapted from DOLMA: a whitespace filter, a language filter, and an alphanumeric filter. We find that deduplication helps minimize saturation as the datastore grows for natural questions, as higher subsampling increases the likelihood of encountering duplicates. However, we notice that the DOLMA quality filters have a relatively limited effect. We hypothesize that this is because the data sources we used in MassiveEDS, like Red Pajama, have already undergone similar quality filtering processes and may not gain much from additional filtering. We then discuss the limitations of our study and potential future directions. While our pipeline allows us to efficiently study datastore scaling, our experiments are constrained by the compute resources available to us. Specifically, our compute optimal scaling studies are limited to model families like Olmo and Pythia, which provide intermediate model checkpoints, as full pre-training runs exceed our budget. Additionally, we conduct the full scaling study with a single retriever, as changing the retriever would require re-indexing the entire datastore. It remains uncertain how variations in the size and architecture of the retriever influence datastore scaling trends. Furthermore, although MASSIVEDS is large, it may still lack high-quality data necessary for enhancing performance on more complex reasoning tasks, such as MMLU and MEDQA. Future research could explore the effects of expanding MassiveEDS to include more diverse and higher-quality data sources. Lastly, our downstream evaluations primarily focus on question-answering tasks, which yield either predefined choices or short-form responses. We plan to evaluate more tasks, such as long-form generation and mathematical reasoning, in future work. Despite these limitations, our research demonstrates that increasing the amount of data available during inference can enhance model performance at a lower training cost across language modeling and various downstream tasks. We anticipate that future efforts to improve retrieval-based models with large-scale data stores will lead to even greater advancements. For instance, our analysis suggests that enhancing the retrieval process, whether through better retrievers or re-rankers, could significantly impact performance. In our acknowledgements, we express our gratitude to Hanane Hajishirzi, Scott Yee, Ian Magnuson, Matt Jordan, and Rui Shin for their valuable discussions. We also thank Stella Lee for her proofreading assistance. PWK is supported by the Singapore National Research Foundation and the National AI Group in the Singapore Ministry of Digital Development and Innovation under the AI Visiting Professorship Program.